Hi, so today I'm reading BERT-of-Theseus, compressing BERT by progressive modular replacing. It's from Wuhan University, Wuhan, Beihang University, Microsoft Research Asia, Beijing, China. So the names are like Xu, Zhou, Ge, Wei, Zhou. Abstract is: in this paper, we propose a model compression approach to effectively compress BERT by progressive module replacing. Our approach first divides original BERT into several modules and builds their compact substitutes. Then we randomly replace the original modules with their substitutes to train compact modules to mimic the behavior of the original modules. We progressively increase the probability of replacement through training. In this way, our approach brings a deeper level of interaction between the original and compact modules and smooths the training process. Compared to the previous knowledge distillation approaches for BERT compression, our approach leverages only one loss function and one hyperparameter, liberating human effort from hyperparameter tuning. Our approach outperforms existing knowledge distillation approaches on good benchmark, showing a new perspective of the model compression. Introduction. With the prevalence of deep learning, many huge neural models have been proposed and achieved state-of-the-art performance in various fields, especially in language modeling and NLP. Pre-training and fine-tuning have become a new norm for most tasks. Transformer-based pre-trained models have dominated the field of both natural language understanding and natural language generation. These models benefit from their overparameterized nature and contain millions of or even billions of parameters, making it computationally expensive and inefficient, considering both memory consumption and high latency. This drawback enormously hinders the applications of these models in production. Okay, let me skip. I would like to find the most, the contributions. And contribution. To summarize, our contribution is twofold. We propose a novel approach, Theseus compression, revealing a new pathway to model compression with only one loss function and one hyperparameter. Our compressed BERT model is twice faster, with retaining more than 98% performance of the original model, outperforming other KD-based compression benchmarks. KD, I think they mean knowledge distillation. Okay, let me go to the conclusion to get the most of the juice of this paper. Discussion and conclusion. In this paper, we propose Theseus compression, a novel model compression approach. We use this approach to compress BERT to a compact model which outperforms other models compressed by knowledge distillation, with only one hyperparameter, one loss function, and no external data. Our work highlights a new genre of model compression and reveals new paths towards model compression. A known limitation of our approach is that to allow a successor module to replace a predecessor module, they must have the same input and output sizes. First, given this restriction, we can still perform depth reduction, that is, reducing the number of layers. As analyzed in paper 28, the hidden size dimension has a smaller impact on computational efficiency than the depth. For fixed parameter budget. Second, there have been developed in place substitutes. There have been many in place substitutes: ShuffleNet unit for ResNet, reformer layer for transformer layer, which can be directly adopted as a successor. Third, it is possible to use feed-forward neural network to map features between the hidden spaces of the different sizes. Although our model has achieved good performance on compressing BERT, it would be interesting to explore its possible applications in other neural fields. As summarized in the table 1, our model does not rely on any model-specific features to compress BERT. Therefore, it is potential to apply Theseus compressions to other large models, ResNet in computer vision. For virtual work, we would like to conduct Theseus compression and computational neural network and graph neural network. Okay, we'll finish the introduction. To resolve this problem, many techniques have been proposed to compress neural network. Generally, these techniques can be categorized into quantizations, Wayne's pruning, knowledge distillation. Among them, KD has received much attention from compressing pre-trained models. KD exploits a large teacher model to teach a compact student model to mimic teacher's behavior. In this way, knowledge embedded in the teacher can be transferred to the smaller model. However, the retrained performance of the student relies on a well-designed distillation loss function, which forces students to behave as a teacher. Recent studies on knowledge distillation even leverage more sophisticated model-specific distillation loss function for better performance. Different from previous KD studies, which explicitly exploit distillation loss to minimize the distance between the teacher model and student model, we propose a new genre of model compression, inspired by famous thought experiment ship of Theseus. In philosophy, where all components of a ship are gradually replaced by new ones until no original component exists. We propose Theseus compression for BERT-of-Theseus, which progressively substitutes modules of BERT with modules of fewer parameters. We call the original model and compressed model predecessor and successor in correspondence to concept of teacher and student in KD, respectively. As known in the figure 1, we specify a substitute successor model for each predecessor module, that is modules in the predecessor model, then randomly replace each predecessor model with its corresponding successor model by probability, and make them work together in the training phase. After convergence, we combine our successor modules to be the successor model for inference. In this way, the large predecessor model can be compressed into a compact successor model. Okay, so once more, it's shown in the figure 1. We first specify substitute successor model for each predecessor model. Then randomly replace each predecessor module with its corresponding successor module by a probability and make them work together in the training phase. After convergence, we combine all successor modules to be a successor model for inference. Okay, let's look at figure 1. A compression training, B successor fine-tuning, the workflow of BERT-of-Theseus. In this example, we compress 6-layer predecessor to 3-layer successor. Contain 1 layer respectively. During module replacement training, each predecessor module is replaced with corresponding successor module by the probability of P. During successor fine-tuning and inference, all successor modules are combined for calculation. So they have 2 phases: module replacing training, which usually it seems to reduce number of layers. They split the model into several sub modules, and then they replace those modules. I'm not sure how they do this module split, but usually in those modules, then they reduce number of layers, and they call that that alternative module a successor, and they train it. They seem to train it, separately. Each of the new successor modules separately, and then they train them also together in phase B, which tries to make all the successor modules to work together. Okay, so related work, I'm going to go fast through this one. Model compression aims to reduce the size of computational cost. Recent work, lottery ticket hypothesis claiming that dense randomly fit forward networks contain subnetworks that can be recognized and trained to get compared to the original network. Quantization reduces number of bits presented to represent number in the model. Weights pruning conduct binary classification to decide whether weights can be trimmed from the model. Knowledge distillation aims to train compatibility behaves like the original. 1. Fitness demonstrate that hints learned by the large model can benefit the distillation process. Born and again neural network reveals that ensembling multiple identical parameterized students can outperform teacher model. LIT introduces blockwise intermediate representation training. Liu et al. 20 distilled knowledge from ensemble models to improve the performance of the single model on NLU tasks. Tan et al. Exploited knowledge distillation for multilingual machine translation. Different from KD-based methods, our proposed Theseus compression is the first approach to mix original model and compact model for training. Also, no additional loss is used through the whole compression procedure, which eliminates the tricky hyperparameter for various losses. Okay, faster BERT. Very recently, many attempts have been to speed up the large pre-trained model. BERT reduces hyperparameter model by necessary heads in transformer, quantized. Use biased information, extract task-specific knowledge from BERT, distill BERT. patient knowledge distillation design, multiple distillation losses between the module states of the teacher and the student, pre-trained distillation, mobile BERT devices are more commercially effective. I think I don't see evolved transformer here. I think the evolved transformer could be mentioned here. I think it's related. Let me know if you think not. They use genetic algorithm approach to evolve slightly different architecture, which is also more lightweight, and I think it also performs better. And I think they do this for BERT there as well. So I think it could have been mentioned here. Let me know. BERT-of-Theseus. In this section, we introduce modular pricing technique proposed in BERT-of-Theseus. Further, we introduce the curriculum learning-driven scheduler to obtain better performance. The workflow is shown in Figure 1. The basic ideas of Theseus compression is very similar to KD. We want successor model to act like a predecessor model. KD explicitly defines loss measure the similarity with teacher and student. However, the performance greatly relies on the design of the loss function. This loss function needs to be combined with task-specific loss. Different from KD, Theseus compression only requires one task-specific loss function, that is cross-entropy, which closely resembles fine-tuning procedure. Inspired by Dropout, we propose modular repricing, a novel technique for model compression. We call the original model and target model a predecessor and the successor respectively. First, we specify a successor module for each module in the predecessor. For example, in the context of BERT compression, we let one transformer layer to be successor of module for two transformer layers. Consider predecessor model P, which has n modules, and the successor model S, which has n predefined modules. Denote predecessor modules and their corresponding substitutes, respectively. The output vectors I, the optician described from. Union compression, we apply modular replacing. Figurative replacing curves of constant module rates. Differentials of gray marked. Okay. I have training samples. The J is the corresponding ground level true. C denote the class label and the set of class label respectively. For big propagation, weights of all the predecessor modules are frozen and only weights of the successor modules are updated. For both embedding layout layer predecessor model are weight frozen, directly adapted for the successor model in training phase. In this way, the gradient can be calculated across the both predecessor and successor module allowing interaction to the on a deeper level. Okay, successor fine-tuning and inference. Since all successor modules have been combined for training, yet we carry out a post-replacement fine-tuning phase. After replacing the compression converges. Yeah, I think we get the gist of this. Although setting curriculum replacement. Well, actually, let me read. Successor fine-tuning and inference. Since all successor modules have been combined for training, yet we further carry out the post-replacement fine-tuning phase. After replacing compression converges, we collect our successor modules and combine them to be a successor model S. Since each SS is smaller than PRD, predecessor model P is in essence compressed into a smaller model. We then fine-tune successor model by optimizing same laws of equation 4 to the whole procedure, including module replacing and successor fine-tuning, is illustrated in Figure 2. Finally, we use the fine-tuned successor for inference as equation 5. Okay, so Figure 2, the replacing curve of a constant module replace rate and a replacement scheduler. We use different shades of gray to mark two phases of Theseus compression. First, module replacing, two, successor fine-tuning. So they have this jump 1, 2, between 1, 2, a linear replace scheduler 1, 2. Okay. Okay, that's gonna be all. Let me know if I should in future read more from the paper. And but otherwise, never ever subscribe or like these videos. Thank you very much, and see you next time. I'm surprised you made it till the end of the video.